Hey everybody, this is going to be a pretty weird quality video. Never done this before, but just want to help you out with capacitors since I know you guys learned that on Thursday, even though I was pretty sure she wouldn't talk about them. So if we go back to what we talked about with resistors, we know that if we have a basic circuit, you have to have a resistor in this circuit. So why do we have to have a resistor? It's because if we don't have a resistor, then the current is just going to be allowed to flow so fast that the wire of the circuit is actually going to melt. So we need to have some kind of resistor in the circuit. And so by that same logic, you can't have just a circuit with a capacitor, because that means, again, this wire will melt. So this is wrong. And so you need to have a resistor and a capacitor in a circuit if you're doing some kind of problem with capacitors. So that's the basic setup. So this would be our battery, this would be a resistor, and this is your capacitor. So one analogy that we used with the resistors is kind of like traffic. So if you imagine cars driving down a road that's congested, if we open up another road, which would mean like a resistor in parallel, there's more options to go down that road, so we're actually lowering the resistance of the circuit. But if we add resistors in series, then you're just adding more and more traffic to the same road, so it's harder for the cars to get down. So that would increase your resistance. So remember, for resistors, we add them in series, and in parallel we add their inverses. So with capacitors, basically we want to do the opposite of that. So we'll say capacitors in series add their inverses, and in parallel you just add them. So to get why we do this, we just need to fundamentally understand what is a capacitor, what actually happens. So I'm going to draw a bigger circuit to make it more visible. So what's actually happening in a circuit? We have our battery here, and remember, we draw our conventional current this way. So we see that positive charges, remember, positive charges don't move, but for conventional current, we draw the positive charges moving in the direction like this. And so these positive charges keep moving, keep moving, keep moving, and we get here, and there's a space, so this wire is not connected from here to here. So we have a buildup of positive charges right here. And so immediately when we start the circuit, the first positive charge is going to flow normally, and this is a neutral plate, so it'll just flow completely normally. However, once that first charge sticks, the second charge coming through is a little repelled because this is a positive charge, but it's still being pushed by a strong enough battery that it's going to stick to that plate. But you can see that as we go over time, we're going to get so many positive charges built up on this plate that at some point the positive charges pushing back this way, pushing back like this, will equal the push of the battery going forward. And so that's when the battery will stop. So let's say this resistor is a light bulb. Initially when we start the circuit, it will be on. And after a long amount of time, when this capacitor is resisting this battery equally, that light bulb will turn off because this will be built up with positive charges, and the opposite side of the plate, which is charged by induction of these, so that means this will become negative, so you're drawing negatives away from here and towards this plate. So we have a negative charge build up here and a positive charge build up here, so then there's just no flow of electricity and that light bulb will turn off. So what do we know about this gap? So when like I had someone ask me earlier, if we build up enough charges on this gap, can it jump to the other side of the plate? So to explain that, I can just give you a real life example. If you think about, let's say the ground of the earth is one plate and the sky is another plate, then when we have bad weather, we have storms, and it gets humid, there's a buildup of water in the air, and we have a thing called a dielectric constant, which in your book you can find it written as K. Your dielectric constant is a property of the material between these plates. So it could be air, it could be paper if you stuff enough paper in between them. It could be whatever it is that's in between those two plates. And when the charge passes that dielectric constant, it can jump. So when it gets humid enough and when the weather conditions get just right, and there's enough charge built up in the atmosphere, that dielectric constant is passed, and that's what we see as lightning. The charge jumps from the sky to the ground, and that's what we see. So similarly, we have air here, and our buildup here is not going to pass that for purposes of this class. So with our resistors, the things we considered were voltage in the battery, the resistance of the resistor, and the current that was flowing through the resistor. Like we were seeing how difficult is it to pass these charges through. That was Ohm's law, which was V equals IR. So similarly, we have a relationship with capacitors and batteries. Again, we have the voltage, we have the capacitors, like the capacitance of the capacitor, and since we have these charges building up, that's what we're also going to measure. So we have charge equals capacitance times the voltage. Now you need to be careful with this because the units of charge are in coulombs. The units of capacitance are in farads, and the units of voltage is in volts. So don't get mixed up with the C of the units of charge and the C referring to capacitance. So now, what this equation is telling us is that we have a certain battery and we have a certain capacitor. Given this relationship, that capacitor can hold a certain amount of charge. So let's say we increase the voltage of the battery, that capacitor is going to be able to hold more charge because it's going to take more of these charges to get stuck on this plate to push back against a stronger battery, because that capacitor is fully charged when it's pushing back equally against the battery. Similarly, if we have maybe a 1 volt battery, it's not going to be pushing that much, so it'll be really easy for this capacitor to equal that push back, and so it's going to have a less amount of charge stored on it.